I have the pleasure of introducing our speaker today, Dr. Maria Gomez. Dr. Maria A. Gomez, professor of chemistry at Mount Holyoke College, received her PhD in theoretical chemical physics from Brown University. She studies proton conduction in a variety of fuel cell materials and teaches physical chemistry and material sciences classes in the Department of Chemistry. Before joining the chemistry department at Mount Holyoke, she conducted postdoctoral research at Los Alamos National Laboratory in New Mexico. At Los Alamos, she discovered that she wanted to pursue research in computational chemistry. Her experience as the only female scientist during lectures at the lab also drove her to encourage women to pursue work in the field. Dr. Gomez was able to accomplish both of these goals. She went on to help found Mercury, a research consortium of 14 primarily undergraduate institutions. The universities in the consortium these universities share computational resources and hold an annual meeting that brings in female scientists as speakers and highlights student work. Dr. Gomez's research has had steady support by the National Science Foundation. Her most cited work includes exploring the role of acceptor dopant on octahedral tilting and proton conduction pathways in perovskites, quantum annealing, molecular realistic solvation models, coupling electronic and phonon mechanisms, and ion hydration. So thank you very much for everyone attending today.
Thank you for that very kind introduction, Ariel. I want to say that it's very inspiring for me to be able to come to a seminar series that is going to be looking at women in science, and to see that already Ariel and others, I'm sure, are sort of doing some mentoring themselves. I'd seen that in your profile. That's awesome. So I'm going to share my screen and then start the presentation. There we go. All right, so I'm going to be talking to you about finding pathways in materials, and I'm going to basically be throwing in a variety of analogies to finding pathways in life as well, and in careers, since this is about looking at personal trajectories in addition to research trajectories. In particular, I want to note that we apply most of these pieces to materials that allow us to have some energy production within them. And this piece that I'm going to be talking to you about was actually done by my fall class. So I taught a class called Using Data Science to Find Hidden Chemical Rules. And so here in this image, you can see the various students that were in this class. And they each sort of took on a particular analysis of how protons moved in a specific perovskite oxide. That's a material that's useful for generating energy in fuel cells. And one of the key things for that material is how quickly the protons conduct. But we were sort of excited. We had turned this class into doing an actual project, and we submitted the project at the end of the semester to the Journal of Chemical Physics. They were doing a special issue celebrating the accomplishments of women scientists in chemical physics and physical chemistry. And so this was exciting because this was a group of all women who are on here, all current students. Some of them are seniors. So for example, Sophia Marcellus, can you actually see my pointer or yes? Okay, good. So Sophia Marcellus is going to be going on to get a PhD in chemistry. She's going to the University of Michigan. But she had a lot of offers, and I'm pretty sure she was leaning towards that one. So I think that's the spot she's headed to. we've got Echo Jiang, who's also interested in going into chemistry, and in particular physical chemistry. I don't think she had decided last I spoke with her on where she was headed. We have Trang Feng, who is was also sort of deciding amidst schools where she was headed. She's going into biochemistry. And we also have some students that aren't quite old enough to have graduated yet within here. And so, their trajectories are still a little less defined. But so basically, I'm just going to take you through some of the work that they did in this class. Some of that work. Now, to be able to understand some of this work, I want to talk a little bit about the structure of these systems, because I realized that I'm talking to I think, electrical engineering department, mostly, or there may be folks from a variety of sciences. Is that right?
It's mainly College of Engineering, but we also have people from physical sciences in here.
Oh, okay. Thank you. All right. So, so the systems that we work with are called perovskites, and this leftmost image shows the geometry of such a system. So it would be an ion in the center of a cube. So in this case, zirconium. So the ZR is in the center. And then at the corners of the cube, there would be barium ions. And then on the very center of the face of each face in the cube, there's an oxygen ion. For the front one, I made it transparent so you could see the ZR that's at the very center. These systems are often what people would call close packed. That means that the size of the main repeating unit in this solid, the unit cell, that's what you have here on the left, is controlled by the ionic radii. So in barium zirconate, the match of ionic radii sum along this diagonal. So looking at the barium's radius plus 2 radii for an oxygen plus the radius for barium again, that sum gives suggests a particular lattice size. And the lattice size would be the length of the side of a cube. And it turns out that the lattice size predicted by that sum of radii is the same as if you were looking at the very center of the cube and looking at the sum of an oxygen radius, a zirconium, I guess 2 zirconium radii, since the zirconium is fully inside, and then another oxygen radius. So this system is very cubic as a result of that match. However, it turns out that the landscape in which protons can move in the system can be altered by small things, such as changing the ZR with a different ion. And so a very common thing that's done is it can be changed for something smaller, but it can also be changed for something bigger. So you have some ions here on the right that are significantly larger. And what I want to point out is what happens when you change it for something larger. So if I took that zirconium ion and put something bigger in that location, then the oxygens that are touching it at the sides would have to move a little bit out of the way, because now the ZR has a larger radius. And so as a result, you end up with a larger distance for a lattice size from this line that's right in the center of the cube. And that would lead to a little bit of an opening along this diagonal, because the entire system would have to expand, not just the line in the center. When that happens, the oxygen that's between the 2 bariums would now have space to move. And so as a result, you could have the oxygen ion move. And I want to point out that the oxygen ion is a vertex in an octahedron, where the ZR, or whatever ion is in the center, is surrounded by 6 different ions for the 6 faces on a cube. And so on the rightmost image, you get to see some octahedra drawn with smaller ionic radii, just so that you can see the geometry a little bit better. And the fact that the octahedra can tilt is a result of the oxygen having enough space along this diagonal to be able to move around. And so that can end up leading to some oxygens being closer together than normal, and so others being further apart because of this octahedral tilting. And that ends up being important because protons are positively charged, oxygens are negatively charged. And so then that means that they'll attract each other. And so the protons will actually want to bind by the oxygens. So you could have, for example, a proton here, or a proton here. So they could bind on different oxygens. And so when the geometry near the oxygen changes, that means that how good a binding site it is for protons is altered as a result of that change. And so in this way, these different ion substitutions, usually people call these ion substitutions as putting in a dopant in the system. And usually you put in a dopant to a very small extent in the system. And so that small amount of dopant can actually lead to some big geometry changes, which can lead to different kinds of possible pathways for the proton to be moving in. So in this paper, what we wanted to do was explore those pathways and to explore them by means of graph analysis. And this is a spot where I suspect that folks in a variety of engineering disciplines often use graphs. And so this might be a little bit more natural than the perovskite pieces themselves. So on the left image is a section of a perovskite, and you can see that we drew in here some octahedra so that you could actually get a feel for how the octahedra are within this section of the perovskite. And then you'll notice that by each oxygen, the oxygens are all in different shades of red. They are protons attached, and we put different colors on them because they're all distinct binding sites. So first, I just want to comment on the oxygen types. In this scenario, there's a scandium dopant that's in this corner where my highlighter is pointing. And then what you notice is that the darkest red ones are all adjacent to that dopant ion. And then the second nearest oxygens are the ones in slightly lighter red. And then the furthest away oxygens in this scenario are in the lightest red, sort of almost pink. So as a result, not only do I have different possibilities for proton binding sites because of octahedral tilting, but I also have different possibilities because different oxygens are at different distances away from the dopant ion. And I want to remind us that in a previous slide, the charge on the dopant ions were all shown to be +3, whereas the original zirconium charge was +4 and protons +1. So you could imagine that a proton would repel less from a +3 charge than from a +4 charge. And so that's partially why you have different types of sites in the system. Now, when we try to map this into a graph, what we do is we consider a particular site. So let's say, for example, this teal one that my cursor is moving by. That each of these sites we're going to think of as a vertex in a graph. And so on the right here, that teal, I'm labeling it as number 4, that's that particular vertex. Now, this teal site, if a proton was there, it could move to this orange site in a single step, or it could move to this brown site in a single step, or it could rotate out of the plane to this gray site or backwards to that pink site. And all of those possible one-step movements are highlighted by an edge connecting the vertices on the graph. So basically each vertex is a binding site and each edge is a connection to another site that can be done by a single step. Namely, there aren't any other sites in between that it could take as shortcuts, because that's the very shortest path you could do. So, so we end up first abstracting from our perovskite system to a graph. And then within the graph, we end up looking for pathways. So we have to sort of pay attention to the fact that while you might have a couple of pathways of the same length, like this one from 13 to 14 to 15, 16, 17, and 18, and another one that's the same length would be this one from 7 to 8 to 9 to 10 to 11 to 12, they can travel different distances because they might take some turns, for example. And when we're interested in proton conduction, we want to actually see it travel through the entire system that we're simulating. So we have to consider both ways that you can move around, consider how likely they are, but also consider the length for these different pieces. Now, supposing I was focused on one particular pathway, in focusing on a particular pathway, there might be a variety of short steps that I might take. So at the bottom here, I've got one particular pathway where I have maybe a rotation, a transfer, a couple more rotations, transfers. And I basically can go through the length of a simulation box, for example. One of the things that would be useful to know is this the best pathway? Is there some other one that's the best pathway? And so those ideas can be partially answered by looking at what's happening to the energy as the proton's moving. And so in the top image is basically an energy profile. So each time I do a type of move, I encounter some kind of barrier, and they could be different, right, for the different types of moves, depending on the specific sites that you're moving between. It could be that a path has a limiting barrier, namely a highest barrier along that path. Such a barrier would be called limiting because it's the hardest jump that the proton has to do. It has to have some energy to overcome that barrier. And not all paths have a single limiting barrier. Sometimes a path can have two barriers that are comparable size. And so both of them might have to be considered. We're going to talk a little bit about how we do that. But at this point, I'm going to take a little bit of a diversion to life trajectories too, because I feel like this also happens in life, right? That you could be sort of hopping along, setting goals, overcoming barriers, and you could get to some really large barrier that you have to overcome. I guess in my life, I have found that it's really useful to have a mentor to help you in thinking about those barriers. And so I wanted to note that your own professor, Charles Thompson, at Bell Labs had done a lot of work with the Cooperative Research Fellowship Program. And I remember having a conversation with him back then where he thought that it was one of the really key features and important pieces of the program was that there be a mentor assigned to each student that was part of the program. And so the mentor I got assigned was John Tully, who you see to the right. And through life, I think that has been amazing for me. I've been able to call John or email him at different points in time when I needed to make a decision, or whenever I had a an issue that I needed to overcome. And so I think one of the things that I see many women in the audience, so I think as a sort of young woman in science, sort of finding a good mentor, I think is really critical to career paths. And at times you might simply be brainstorming with them. At other times they can help you make new connections. All those pieces are really important. I'm really lucky. I've had many mentors who have been wonderful. Professor Jimmy Dahl was my PhD advisor, and Professor Lawrence Pratt was my postdoctoral advisor. And all of them really were very helpful. Some in sort of giving me confidence at times, and at other times just sort of connecting me with someone that could help me solve a particular problem I was looking at. And I think probably it's, I guess I'll just say that it's a normal thing to encounter barriers. I think that every student that I've had once they go to graduate school has called me at some point from their school, sort of asking about some issue that they've had. I'll note that I myself, had issues as well. There was this quantum mechanics class that I had wanted to take in the physics department, where I had gone to grad school, and the professor there, when I went to speak to him before I took the class, I think it was during the summer, had told me that that I probably didn't want to take his quantum mechanics class. And I was pointing out that even though I was in the chem department, that I had gotten an undergraduate physics major, and I was very confident that I was ready for this class, and I really did want to take it. And after my pushing a bit, he told me, well, I've never had a woman succeed in my class. And that was, that hurt, I guess. I did sort of point out to him that I knew I already had some quantum mechanics classes. I just wanted this particular piece that I wanted to look at next. And in the end, I couldn't really make him budge, but I think because I already had, I had already had conversations with John Tolley, I had already had conversations with Jimmy Dahl about sort of barriers that I might have to encounter at some point. I just told him, well, I don't think you can stop me from signing up for your class. I've got all the prerequisites required. I'm only here because I want to know what textbook you're using. So in the end, I took his class. I was the only woman in the class. That didn't surprise me after the reception I had had. But I think that sometimes you need just to be stubborn, right? So to be able to hop over a barrier, you have to have the energy to do it, and also you have to make lots of attempts at doing it. I worked very hard in his class, and in the end, he well, I'm not quite sure exactly sort of what necessarily went through his mind, but at this time, grades were always posted at the door. And so I know that at the end of the class, I had the highest average from anyone else in that class. But he was a tough cookie, that professor, the whole ways. But I think if I hadn't had people that had believed in me before, it would have been very hard to go through that that experience. And so maybe the lesson there is you have to be stubborn. To go over a barrier, you got to put in a bit of energy, but you also have to attempt it a bunch of times. So sort of the one sort of life piece that I've put in here. Once we create a graph for our perovskite system, the next thing we do is consider methods for finding pathways through the graph. And so some of them are pretty standard things that people do in graph searching. We might start at some particular vertex, let's say I1, and then we could consider all the possible connections from that vertex. And then for each of those possible connections, we can look at connections again. When there's no more spots to go to, that could be a sort of dead end in our trajectory. But there might be some that get us through many more steps. And at the end, we check that the final step that we're considering has actually allowed us to travel through the whole simulation box. So that's sort of just a way of finding the pathways. But another aspect is, how do we weight them? Which ones are more important than others? And so to do that, we consider that there's some rate constant for moving between different sites. And usually that involves going over a barrier. So there might be an exponential that has a barrier in the exponent that you have to hop over. And in the main part of the equation, there could be some frequency, something related to frequencies that relates to how often you try to go over that barrier. We calculate these rate constants by basically solving the quantum mechanical problem to get the energies and the frequencies. And then after that, we calculate probabilities between sites, assuming that the probability to go from I to J is proportional to the rate constant to go from I to J. And then the proportionality constant is sort of this division piece here, which is about all the ways that you could escape that particular site I. Once we have probabilities, we calculate weights on edges. And the weights on edges are just minus the log of the probability. Part of the reason for doing that is so that the edges are additive, whereas probabilities are multiplicative. So in general, the probability for a particular path might be the probability that you start at a particular point, and then the probability that you go from that initial point to the next point, and so forth. And if I took minus the natural log of that, I would end up with the weight for the overall path as being sort of a weight of being at the starting point plus weights for doing all your different moves. So, so we did that. And with that, then we were able to find different types of trajectories. And so on the right, you can see that in this trajectory, there's this arrow that's a little different shape than the others. That's the limiting barrier along the path. And you can see that on the trajectory on the left, there's two of those. So there are actually two that are similar in magnitude. And so there's a path that has a couple of limiting barriers. These two paths are for, the one on the right is a yttrium dope system. So this teal ion is the yttrium ion. And what I wanted to notice about this path is that the path is on a plane that has the yttrium in it. So it actually tries to stay near the yttrium through the whole path here. Whereas on the one on the, oh, sorry, this is the right. My apologies for that. So the other one that's actually on the left has the scandium ion, and that's this purple piece. And what you can tell here is that the pathway is on a plane that does not have the yttrium. So the yttrium is in this front plane, and that back plane doesn't actually have it. But the path is along that plane. So, so in this way, we could sort of get a sense that the trajectories have a different feel to them. I want to note that there's actually lots of paths that have similar probability. So here I'm showing the highest probability path, but there are actually lots of others that have the same probability. So it could be thousands, for example. So in a sense, you might say that, that a good system, or a system that conducts protons really well, could be resilient. It has lots of ways for the proton to move through quickly in the system. It also has some ways through which it can move through more slowly. But that resilience is useful because it means that if one path is blocked, it can still take others potentially to get through the system. All right, and the paths do have some common features. Now, because there's so many paths, there's thousands of paths, in fact, one thing that we hoped is to be able to create some picture that gave us a feel for everything that could occur in a system all at once. And so for that, we end up using what are known as centrality measures. And for this, we basically just, we started off with an old probability book by Grinstead and Schnell that had a discussion of centrality measures, or basically points that are central to a graph that you might move about often. But we had to make some changes from the traditional method because in the traditional method, you only considered the total number of steps in a path. Whereas for chemical systems and lots of other physical systems, the barriers can be different. And so that means that the steps are not all equal. Some steps are harder to do or slower than others, and other steps are easier to do and faster than others. So, so we use this centrality measure from Grinstead and Snell, and I'm not going to show you everything, but I am just going to give you a little bit of a flavor for what we did to change things. So Grinstead and Snell first talked about a mean first passage number of steps to go from I to J. So imagine that this site is I, and this other site might be J. So you could see that I could go from I to J, in this case, maybe in a single step, or it might be that I take multiple steps to get there. And so Christian and Snell thought, well, this is actually an important piece to see what the average time in terms of number of steps is for going from I to J. If that time or number of steps is really small, then that suggests that this is an easy move to make. Then if it's really big, this is a much harder move. And so we could later use this time to eventually get us to a centrality measure. So Grinstead and Snell had a way of calculating this mean first passage time. That variable for the mean first passage number of steps is mi sub j. And so they said, well, this is just an average. So if this is just an average, then what that means is that I should consider in this average looking at the probability that I do it in a single step. And so let's say that'll be one step, and multiply by the probability that I can go from I to J in one step. But then I also have to consider the possibility that it takes me more than one step. And so then I would have to consider that I might go from I to some other point, let's say L, in a single step. But afterwards, it would take me other steps to get to J. And so then I would multiply this probability that my first move is to L by the total number of steps that it might take to go from I to J. And that would be 1 for going from I to L, and then MLJ for going from L to J. And then you can consider all the possible L such that L can't be J. So that's what that first equation is. And the only change we made was basically to take this number 1, which referred to a single step, and instead of thinking about it as a single step, we wanted to put a time in that spot so that we would have a mean first passage time instead of a mean first passage number of steps. So as an estimate on the time, we chose to invert a rate constant, because the rate constant is the number of steps per unit time that that you might do, or the number of times you might see something, a particular step per unit time. And so the inverse is the average time to see that step in effect. So this time we took the probability of going from I to j directly, and we multiplied it by the average time, or 1 over kij, to go from I to j. And then in the second piece, we took that average time and we added it to the time to go from L to J, figuring that we were now going from I to L in one step. And so we looked at the average time to go from I to L plus the average time to go from L to J. That was the main change that we did. Otherwise, we kept things pretty much the same as Grinstead and Snell did. And so from that, we could begin to consider going from I to J and then coming right back, went from J to I. And we're going to call that the round trip time to go from I to J and back to I. And then in principle, we could add up all the round trip times, divide by however many there are. So effectively, we could average the round trip times. And that would give us the average round trip time to go from I to any j and back. And the inverse of that average round trip time is the centrality of I. So if you start at some vertex I, and you allow the proton to move to some other vertex, and you wait for it to come back, the average time that it takes to come back, if that's really long, then that means that that site is not very central. So it takes a long time to get back to it. But if that time is really short, then that site is more central. In terms of physical aspects, it might mean that if you have high centrality, then that might mean that the site is a trap. It might actually be that you can get a little bit away from it, but because there's some large barrier preventing you from going too far from it, you can return to it often. And so that would be one possibility for having a highly central site. Another possibility might be that it could be a good connection or a nexus between many different paths. And so it could have high centrality for that reason instead. So, all right, so basically then we made a picture of our systems, and we made a shading on the sites based on centrality. So if the sites were really central or important to the system, we made them black. And if they were not very central or not so important to the system, we made them white. And gray is all the things in between in principle. So in the top image, so the top image is for a system that has scandium as the dopant, and the bottom one has yttrium as the dopant. And in the top image, one of the things you can see is that there's a trap right around the scandium dopant. Namely, there's high centrality pieces. You can move very quickly as long as you stay near the dopant. But it actually takes a lot to move away from the high centrality pieces because the next sections are low centrality segments. And if we look at a plane that doesn't have the scandium dopant, but still in the same system, you can have some highly central sites on those planes. And the highest barriers tend to be movements away from those central sites to the next spot. The highest barriers along a high probability pathway, that's what I should say, seem to move you from high centrality sites to the next possible centrality site that you could be in. In the yttrium system, however, there's a high centrality connectivity that's in the plane of the dopant. And so that seems to be why pathways actually like to be by the dopant in these scenarios. So that was exciting, that so we could actually sort of map where the high probability highways or the high probability pathways would be using this centrality approach. Right. And so that's sort of the main pieces of that story that I was going to point out. And I was just also going to give you a flavor of other kinds of things that we've done. We've also considered other types of defects in systems. So not always dopant defects, but although there can be dopant defects within other scenarios. So here in these boxes, I've got a dopant, and as you go towards the right, the dopant is getting bigger. And so you can see that the shape of that little section of the system looks very cubic on the left, and it looks less cubic as you go towards the right. There's more distortions in it. And that ends up affecting how the system can handle an oxygen vacancy, for example. We were interested in that because experiments suggested that you could actually speed up conduction in the system in the center, which has the scandium dopant in it. That's the one that seemed to have a very significant trap based on centrality in the previous image. But if you actually put an oxygen vacancy in such a system, you can actually lower the barriers in such a system. So here in this table from this text, this basically is a variety of moves that are often the limiting barriers. And so for scandium, you can see that without the vacancy, the barrier might be 0.53 electron volts, for example. But when you introduce the vacancy, you can actually go down to like 0.10 EVs. Now, this is the barrier that's very close to the vacancy, though. So it's not, if you're further away from the vacancy, you might not see such a big change for a particular type of motion. So sort of one study we did, and these are the students that did that work. Miriam Valerio is now at the University of Santa Barbara working on her PhD. Janie Lin is at University of Chicago. Shiyun Lin is at University of California in Los Angeles. Yuan Tian is at Harvard, and Alice Van Boekelen is, so in addition to having chemistry as a passion, horseback riding was a passion for her. And so she now has her own sort of training center for horseback riding. So she's sort of pursuing something a little different, but these are the various students involved in that work. We've also looked at some scenarios where we simply look at the geometry of systems and how that's affected by a vacancy. So in this image, you could have an octahedron, and you could be missing, let's say, this corner oxygen. And because there's a positive ion in the center whose charge is screened from other positive ions by the oxygens, one of the things that can happen is you can have the oxygens move to basically change the geometry. So you can go to trigonal bipyramids from initial partial octahedra. And you can also have rotations assist to basically, instead of having sort of in this plane, sort of 4 oxygens connected to an ion in the center, you could end up having 5. And that could be helpful if either, for example, the top oxygen or the bottom oxygen were removed as a vacancy. So, so this was kind of exciting. We did a collaboration with Roy-Hem Kim, who actually did measurements on these things. And he saw that in fact, you do see significant distortions in both calculations and experiments. And then the undergraduate students worked on this were Megha Patel, who is doing some research in neuroscience currently, and is thinking of going to med school, and Jiayun Zhang, who is at Yale in the Department of Chemistry there. And actually, maybe I should say that she's in Sharon Hem-Shepard's group, and Sharon was not in the CRFP program of Bell Labs, but in a I won't remember the exact initials for it, but in another program, Bell Labs also had John Tully as a mentor. And this paper is sort of exciting for me. My son, this is Conrad, actually got to participate with me on that too. So that was pretty cool for me, at least to actually have him do a project with me. And we also do collaborations with other labs. So this year we collaborated with Claire Gray and Celine Merlet. Claire Gray is a NMR spectroscopist. And Celine Merlet used to be in Claire's group and now has her own position. And with them, we looked together at trying to understand local distortions that both computationally and experimentally. And we've also collaborated with the group of Quan-Li Chen, who is a professor in China, and Arthur Braun, who is at a national lab in Switzerland. And the undergraduate student that worked with us then is Hu Pan, who is now getting her PhD in computer science in University of Australia at Perham, maybe? I should have written it down, but in any case, she's in a PhD program herself now too. And that was basically the pieces I planned. Want to be sure that we had some time to have you ask questions about either trajectory or physical pathways. Thank you for listening. And I also want to thank our funders, National Science Foundation, through a couple of different grants currently.
We'll give you a hand from Zoom here.
Oh, thank you. Actually, you know what I should do? I will sort of maybe do one other thing that I was excited about showing you. If I can, let's see. Here we go. I'll end the show. And here, so I was mostly just tell you about some former students. So this is Saryu Fencing, who is there getting a Young Leaders Award for Minerals, Metals, and Materials Society. She is at Los Alamos National Lab now, one of the staff members there. They did some special feature on her in their site. And it was exciting because back when I was at Los Alamos, I hadn't seen many other women other than our administrative assistants, who were wonderful. But I think towards the end, there was another woman who came in to the area that I worked in, but I hadn't seen so many. And so I asked, are you about now that she's there, how are those numbers? And so she is in a group of 50 people, and they have 5 women. So like that's an improvement, right? That's exciting to see. Another former student, Mayan Ha, is at NREL National Labs. So that's National Renewable Energy Laboratory. And they also did a feature on her. She, her passion for research, and she's actually sort of taking on her own undergraduate students during the summer times, which is exciting. She's doing a postdoc there currently. And before I was at Mount Holyoke College, I was at Vassar, and my first student was Valentino Cooper. He was actually a fantastic person to have as first student, and now he's a distinguished research and development staff member and section head in materials theory, modeling, and simulation at Oak Ridge National Labs. He's a superstar. He's done some really great things. And from Vassar, also Damien McCarty is at the National Institute of Standards. So it's exciting. And Mount Holyoke, Caitlin Scott just started as an assistant professor at Hendrix College. So this isn't everybody, there's a lot of people, but I thought I would just sort of give you some highlights of students as well. Now I'll go ahead and take your questions.
I had two questions, and one was really the culture of undergraduate research at your institution. Clearly, you see very successful young women who probably started early on. So could you speak a little bit about, is that specific to your group, or is there a larger culture at Mount Holyoke that encourages undergraduate research?
There is, I mean, I was very lucky to arrive at a school that had a very large culture of undergraduate research. In fact, my first student at Mount Holyoke was Saryu, and she contacted me before I arrived, basically noting it was that she was excited about the research, so based on the talk that I had given when I had interviewed. But she was also sort of nervous because it was so difficult to get into research labs. And I have to say, now that I've been there, that is maybe one problem that we have. I guess it's a good problem for faculty, but maybe challenging for students. It's simply that there's such a culture that there's a lot of competition to get into research labs on campus. So we try to find a home for each individual, and if it's not quite possible, just based on interests, we also try to make sure they can go to other places, right? And try to do some summer research experiences at RUs. As well. And actually, for that matter, even the students that I have in my lab, they might do research with me during one summer and during the academic year, but in later summers, I try to send them to another person so they can get a feeling for what it's like to do research in another place. But in terms of like how, I'm not quite sure how that culture came about, since it existed before I got there, but my colleagues tell me that I guess it was just Mount Holyoke students were very dedicated and just really, maybe it's a peer pressure thing, right? I think if you have a set of students at some point in time that set up this culture, then the others sort of come along too, because of that peer pressure that they find within there. But the tough part is that we do still have some really great students that happen not to sort of get into a lab. And this is maybe one of the reasons why we try in some classes and some electives and in some maybe junior and senior level classes to try to have some research-like experiences within the class, so that at least there's some taste for research at that stage.
Okay. And my second follow-up was, your work is computationally based. So is there an underlying training or a curriculum set up for all students to have some computational modeling experience?
So through our curriculum, so starting with general chemistry, we have we have one lab within general chemistry that's computational right now, just to give them a little bit of a taste. But it's certainly not enough, I would say, in terms of sort of training. So usually when someone's interested, we end up doing some training just as they're doing the pieces. So we do try to incorporate in each class of the curriculum some perspective on different areas that faculty do research in. But there are always additional pieces. We try to bridge some of that with electives, I guess. Each faculty member has an elective or a couple of electives that could serve as training for their group, in a sense. And we try to make the requirements for those be sort of low bar type things, so that many students can take them.
Okay. I'll open it up to the audience. Questions for our speaker? I
have a comment.
Go ahead, Natasha.
That was an awesome presentation. Thank you for sharing.
Thank you.
Thank you. Thank you. I'm excited.
I have a question.
Sanjeev. Yeah,
I have a question. Excellent, absolutely excellent presentation. Thank you. I didn't know what to expect in this talk. I just signed in, and it was absolutely brilliant. Thank you for a great presentation. Now the question. You're using the dopants to create pathways for proton conduction in your system. That's really remarkable. I work on materials that we also dope materials, and then to create pathways for electron conduction.
Oh, cool.
So for conductivity, So I'm thinking, I'm getting a lot of ideas from your talk. Maybe we've missed something in electron conduction that we should think about with respect to the dopant. The question is, I had a very mundane question with this. You said that the pathways are close to the dopant, right? I mean, pathways are created close to the dopant. But if the dopant is positively charged or the proton is positively charged, would you not repel? And so the pathway should be as far away from the dopant as possible, right?
That's a great question. So let me, I think you can I'm still sharing screen right then. Okay, so I'm gonna make this big and just the side here. Okay, so I guess I'll say that whether or not the pathway is close or far from the dopant depends on how large the dopant is. So for scenarios where you have a really large dopant, like yttrium, in those cases, you end up with these distortions from cubic, where some oxygens are closer together, for example, like this one and this one, than, for example, this one and that one. Whereas in the scandium case, that scandium is actually very close in size to the original ion. In that case, you can see that this looks a little bit more like a square than in the yttrium case. And in that scenario, the path is actually on a plane without the dopant. So it seems like the dopant's main effect is that based on its size, it can allow or not allow oxygen vertices that are on an octahedron to move. If they can move, then that movement seems to help with the stabilizing of the defect in the system. That seems to work both when you have an oxygen vacancy as a defect or a separate ion that we've put in as a dopant for the defect. And that stabilization can, so I guess maybe I'll note that in both cases, the dopant is +3, whereas the zirconium would have been +4. So in both cases, things prefer to be close to the dopant ion, and there can be barriers to move away from it. However, when you can have tilting in the system, that tilting can help to stabilize the defect. And that stabilizing of the defect seems to lower some of the barriers that would have made that defect a trap. And when you don't have tilting, it's not really possible to stabilize the defect so well. So it depends on the particular defect size in addition to its charge.
Thank you.
You're welcome.
I had a question. So I was wondering if you had any advice for, undergraduate students looking to get into research, how they should go about it and what they should do once they're in a lab.
Well, that's a great question. So my advice, if you're interested in joining a lab, is to, I guess the first thing is look through the department web pages, right, for the department that you're most excited about, probably the one that you're in. And then to send an email to the professors that whose work you're most interested in based on what they've placed in their web pages. So not just to one of them though, to send it to a few that you would be potentially interested in working with, letting them know that you took a look at their sites, what excited you about those sites, and seeing if you could meet with them to discuss the possibilities. You could note that you understand that for some labs, you might need to take a certain class beforehand. So I would definitely encourage people to do this early before they might even think that you might say, well, I might want to do this particular year, but it'd be good to be doing the contacts earlier so you could take whatever class was necessary to potentially join that lab. I think professors, being human, are very susceptible to just feeling happy that somebody was excited about their work, and that I think can have some really good, it can have a nice outcome as a result of that. I suggest doing it with multiple people just because to some extent through this, you're also testing them. Right? If they don't respond, that's a bad sign. I would probably sort of write again in case it's simply that they missed it amidst a whole bunch of emails. But you do want an advisor who's responsive for sure. So that's an important piece. And I would also apply to REU programs. So on the National Science Foundation page, there's an REU link that tells you about the REU programs everywhere in a variety of disciplines. And so those are ones that are specifically calling for undergraduates. And so I would look at those as well. Now, we have a lot of international students at Mount Holyoke, and so if you're an international student, a lot of the RU programs say that you can't apply there. But what we have found is that sometimes if it's a SURF program, they seem to be more flexible in some of their funding. I'm not entirely sure why, but some of them have taken some of our international students. And the other piece is simply using your contacts. So you might have a professor that you've gotten to know well based on classes. You could ask them about potential opportunities as well. They could be a good option because if you're excited about their class, then it's good likelihood that you'd be excited about the type of research that they do as well. And the squeaky wheel gets the oil. You want to ask, and you do want to ask a couple of times, perhaps, and find out about it if it's a timing thing. Well, maybe there's no space in the lab now, but there might be some later. There'll be some class that could be helpful to be able to do this later.
Maria, when you were an undergraduate, you were successful in receiving 2 prestigious fellowships, right? You got the NSF, the GRFP, and as well as the CRFP. Could you talk about what made you apply? What do you think that was in your profile that was helped you be successful in receiving these awards?
Actually, Professor Thompson just revealed something that he was apparently on the pool that was making those decisions. So, all right. So I would say that that one of the things that was helpful was that I did do undergraduate research. And so I wrote about that within the application. And I think it's important to make sure that people can see how excited you are about the research, and to see your excitement about your future plans in the area that you're interested in going into. So those pieces are definitely important. I think it's a lot of times we hear about these programs because of mentors and advisors. So I would also recommend simply going to advisors at this stage and sort of finding out what programs they know of that are available, might be applicable, and doing some good searches on those pieces as well. I think it's always a good thing to give yourself to make sure that you covered lots of areas in your discipline, just as in general, because these programs also get your transcripts, and you'll do as well as you can. Letters of recommendation, I think, are looked upon really as a big piece within there. So you want to be sure that you ask recommenders, ideally ones that you've done some research with, but you also want to be sure that they're willing to write you a strong recommendation. Part of that, this part I wasn't so savvy about, I think, beforehand, but I see some of my students are pretty savvy about it, and that is, I love it if a student sort of comes and asks me for a letter. I love it when they help me to some extent. So there might be things that I can definitely say about them based on the classes I've had with them or the work that they've done with research with me. But there could be some other experiences that they've had that I don't know about. And so it's really helpful from the perspective of the recommender if a student sort of puts together some of the pieces that they think should be emphasized in a recommendation letter. So helping your recommenders, I think, is also a piece of advice that I would give.
Thank you. Any other question from the audience?
I have a couple of questions.
Lana, go ahead.
How do you balance everything that you do with your coursework? For me specifically, sometimes it's just a lot. I have a hard time in school. I have to dedicate enough time to that, and I have to pick and choose what I do and make these sort of decisions. How do you choose what's most important to you, and how do you balance your research with being an undergraduate student?
That's a great question. So I think that maybe finding that balance has been different at different points in my life, I would say. So back when I was a student, I would try to, I did have jobs back when I was an undergrad, but I would try to make sure that those could be ones that could contribute to me as a student as well. So that was one way to help myself to keep balance within those pieces back then. Later, when I started grad school, I guess there's some people that I think can simply work for a really long time and not be tired of it, but I needed breaks myself, right? I think I needed sort of time away from things to be able to think about other things, and that would allow me to be fresher afterwards. So I think having an advisor that was very understanding helped, but I basically tried to schedule my work so that I would have some bursts, but then I would have some slower times in between so that I could, go for a walk, right? Or just do something a little different for a period of time. Even just switching the project that you're working on, I think can help out. But having, I think, breaks was important. And then eventually later when I became a mom, was probably when that balance was the hardest to do. But I guess when I chose the type of school that I went to, I partially chose it thinking about the time that I would have and what I would be able to do. So I picked it certainly thinking that I wanted to influence young women to go into science. But I also picked it making sure that it was, or trying to be sure that it was a friendly place to be at. And I know surprisingly, sort of even in interviews, you can find some of that. So there was an interview that I went to where so that was a school with a graduate program where some of the folks told me that there was a lot of pressure on them to hire women, but a lot of people were resistant to having another woman on faculty. I wasn't going to be the first. There was like one other person there, but that was, I guess, it was a red flag for them, I suppose, but it was a red flag for me too. Right? That this might not be a really great spot. Because even though I'd been at places where at Los Alamos where there weren't other women, nobody told me at the interview there that they were hesitant about that. Right? Whereas at this other place, they told me that, and so that was a red flag for me. I didn't think life-work balance would work very well when they were already hesitant about that. So having a place that had that was sort of interested in promoting a good work-life balance, and I guess I'll say that this piece is true for men too, in the sense that if men and women will become parents, to have more equal sharing, that means that both people have to have somewhat flexible jobs. And so at Mount Holyoke, there was a daycare on campus, and that was really helpful, right then, because it meant that I wouldn't have to go far, right, to pick up my child, right then, when I needed to get him. And I also had been told stories by others that they had just, when they couldn't do anything else, they just brought their kids in. Right? And I did that too. Right? There were times when that was simply the only option. If there was some sort of school closure and had to bring in your child. And so having a place that's accepting of that is important. Some people try to sort of keep their work life and their personal life fairly separate and find that helps. For me, it was the opposite. I actually thought it was helpful to be able to choose some things within my work that would be helpful to my family. So since we always have to do some sort of outreach with grants, when my son was small, I chose the outreach to be setting up these kits that were given to public libraries in the area and that parent-child teams could check out to have this little adventure with their child. And so that was helpful because I knew I took my son to the library when he was a preschooler, and we would check out a variety of things from there. And at some point he said, "Oh, do you think they would have like a chemistry kits we could check out, Mom?" Well, maybe not, but maybe I could make such things. Right? And so So I basically try to also pick some things that were going to help me, because since he was my tester, that meant that while I was doing work, I could actually be doing something with him too. So, so looking at ways to do some things count twice in a sense, was helpful for me. And the other piece that other people gave me this advice, and that's in terms of preparing for class. And what makes a good class is a lot about the interactions that you have while you're there. And so while you can be really tempted to work, not to say that you don't want to work hard on your lecture, you do want to work hard on your lecture, but after a certain amount of time spent on it, it's diminishing returns. It doesn't really get better after some point in time, because so much of it is about what's actively happening with you and your students in it. So what someone had suggested to me, and I did do, is to set myself a time limit, right? So I had some time to prepare for class, and I was just going to use that amount of time. And then I was going to move on to the next thing I needed to do. I think that was helpful for me as well.
Thank you very much.
You're welcome.
All right, so we will, unless there's another question from anybody, I will close the Professor Thompson, did you have a comment or a question?
Can you hear me?
Yes.
Well, it was 17 years ago. We didn't make a mistake. We didn't make-
Well, thank you. And I always have to say, I'm definitely very thankful for it.
Well, we're thankful for the things you've done too. And you, I think many of the students maybe have idea, perspective, and set their objectives, based on what you said today. And maybe that will be a turning point for them to consider research. All I can say is that in her case, she identified, I think, I read a lot of them, but I would say that in a very clear way, what her passion was. Okay. And I think, as an undergraduate, you should really try to find that thing that you're really passionate about. And REUs and all that stuff are supportive of that. But ideally, if you can find what you really are excited about, you can get other allies to join you, to support you to meet your objective. I think Maria did that in her application. Okay. So I thought that was unique. So since I haven't talked to her like almost 20 years, I should at least say that I think her passion came out, and I hope that many of you students can find that as well. Maybe get some help from some faculty members and others as well. All right, thanks, Maria.
Thank you. And I have to say, I would love to see that sort of list of others in the CRFP program.
I'll give you a link.
Thank you.
Okay.
I appreciate it.
All right, take care of yourself.
Thanks.
All right, Ariel, we're ready to close.
Yes, I think so. I can send Dr. Gomez the link, Professor Thompson. I know where it is. I can send it to you afterwards.
Mm-hmm.
Thank you. And thank you, Ariel, for already sort of reaching out to others too and mentoring students yourself. And that's awesome.
Yeah, I'm grateful for the opportunity to do it. It's exciting. I like working with people, so I'm grateful.
That's awesome.
And Maria will share your email with the students who might want to reach out to you.
That would be great. That would be great.
Thank you very much.
Take care. It was good seeing some of you again and meeting all of you. Take care.
Thank you.
Have a good one.